So this is lesson 11.1, part 2. We're going to continue to work with the fundamental counting principle today, but we are formalizing things and starting to talk about what we call permutations. We're also going to formally introduce you to factorial notation, although I have informally done so yesterday. I think this is on page 8, isn't it? Yeah. So we're going to use factorial notation to evaluate expressions, solve problems using a formula for permutations, and then solve equations involving permutations. Don't worry about that notation in the third bullet. We'll get to that in a bit. So consider the total number of ways of arranging 7 books on a shelf. This is not a difficult question. We would, if you wanted to use the fundamental counting principle, you would say that. This is what your thought process would be. You would say, I have the first place, second place, third place, or first position, second position, third position, etc. So the number of ways to do that would be 7 times 6 times 5 times 4 times 3 times 2. I know we do not need to say times 1, but we write it in mathematics. And of course, from yesterday, we know that that's written as 7 factorial, 7 with the exclamation point. And on your calculator, if you calculate 7 factorial for me right now, and I know that many of you have learned about the alpha menu. My alpha menu is different than your alpha menu, so I'm not even going to use it because some of the things are there and some of them are not on my calculator. I'm going to go to the traditional place of finding the factorial notation. So I enter 7, I go math, I scroll over to probability. I could scroll right, but I just scroll to the left once and the factorial is there. I don't believe I showed that to you yesterday. I think I showed it to you in the alpha menu, and I said, and if you don't have that, I'll show you where it is. Well, now I'm showing it to you. I think it's 50-40. So there are 5,040 ways of arranging 7 books on a shelf. But in general, and this is Math 30, so we want to kind of get a little bit more abstract here. When I talk about n factorial, algebraically, I can write n factorial as n times n minus 1 times n minus 2 times n minus 3, and I keep subtracting 1 from n until I get down to 3 times 2 times 1. And I understand that some of you might look at this and go, well, that's not really going to fit for something like 6 factorial. Okay, maybe I have too many terms there. This is just a general statement. You would adjust it for each factorial. So calculate the following. This is just getting you to use your calculator. I would like everybody to find 5 factorial. 7 factorial we've already done. It's 50-40. I believe 5 factorial is 120. After a while, you know how in earlier grades in math you learn about squaring? I'm talking really early, like junior high-ish. You learn about squaring numbers, and sooner or later you go, oh, wow, 7 squared is 49. 9 squared is 81. Sooner or later you'll say, oh, well, 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. I usually can get up to 7 factorial, and then my brain just says, I better calculate it to be sure. B, explain why 50 factorial over 48 factorial is equal to 2450. So maybe what I want you to do is I want you to see if you can figure out a way to calculate 50 factorial over 48 factorial without using the factorial key and without going 50 times 49 times 48 times 40, without doing that. And this is typical when I ask this kind of question in a lesson. I'm just curious. I'm asking you to figure out, can you figure out what that quotient is without using the factorial key? If you've got an answer, put your hand. If you know how, put your hand up and then down. And the key word or the key part of the word factorial is factor. When I say 48 factorial is 48 times 47 times 46, etc., I'm saying in 48 factorial there's a factor of 48, there's a factor of 47, there's a factor of 46, etc. How would we do this, Brody?
Well, so in the 50 factorial there's factors of 48, 47, 46. So it's the same as the 48 factorial.
Right. And in fact, I'm going to write that out symbolically. It's a hard thing to put into words. If I write it out on paper, 50 factorial is 50 times 49 times 48 times 47 times 3 times 2 times 1. But this is 48 factorial. And the denominator of this is 48 factorial. And what I'm getting at is that the smaller factorial is a factor of the larger factorial. So it cancels. That's what I've been trying to impress on you whenever we talk about rational expressions. You factor and cancel. You can only cancel things that are factors. So this cancels with this, and you're left with 49 times 50. And if you multiply 49 times 50, I hope you're going to get 2450. Okay. I mean, I could, and you might say, well, yeah, I could use my factorial key. I don't need to know that. Well, you do need to know it for later on when we talk about algebraic expressions. But to give you an illustration of, I really don't think I would give this to you on an exam as a single question. I think it would be part of a bigger question. If I said to you on an exam, I better not go crazy here. If I said to you, what is 72 factorial over 70 factorial? It's a good numerical response question now that I think of it. Your calculator can't handle those factorials. I don't think we've talked about this. If you try to take, I think 69 factorial, your calculator can eke out an answer. It's going to be something point something times 10 to the 98 or 99. It's going to be this huge number. And your calculator's memory, the programming limits the memory to numbers below or up to 9.99999 times 10 to the 99. So 70 factorial is too big, 72 factorial is too big. If you try to enter that into your calculator, you will not get the answer. But the answer is whatever 72 times 71 is. Which would fit in a numerical response. Again, I don't think I would ask that to you, but you never know. Okay. So simplify each of the following. Well, now we're getting into exam type of questions. This could be a numerical response question. I would have to tweak it a bit, or a multiple choice question. I hope you would agree that the factorial on the top is a larger factorial than the factorial on the bottom. N is a bigger number than n minus 2. Just like, was it 50 and 48 in our example? Just like 50 is a bigger number than 48. So when we had 50 factorial over 48 factorial, we took the factorial that was bigger and expanded it out to see the other factorial. So that's what we're going to do here. We're going to take n factorial and expand it out. N factorial is n times 1 less times 1 less times 1 less. You don't need to put everything down that I'm putting. You could have stopped at n minus 1 or n minus 2. Put your ellipsis, which means on and on and on and on. And then I typically will go times 3 times 2 times 1. I think that, although I might think it's lazy, I think diploma exam markers might think it lazy to just write that. I think it's more impressive for the markers to see that. Divided by n minus 2 factorial, but n minus 2 factorial is that. So what cancels is the n minus 2 factorial with the n minus 2 factorial, leaving us n times n minus 1. And you could certainly multiply that out and write n squared minus n. B. n plus 3 factorial over n factorial. Well, which is the larger factorial? N plus 3. So we have to expand out the n plus 3 factorial until we see inside of it somewhere the n factorial. Well, n plus 3 factorial is n plus 3 times 1 less, which is n plus 2, times 1 less, which is n plus 1, times 1 less, which is n. How many of you see that that n and everything down to the end of the line is going to cancel? Okay, that's the point. I'm going to put just a couple more here. You can decide if you want to put more or less. It's up to you. And again, I would highly encourage you to put times 3 times 2 times 1. This, of course, is over n factorial. But from here down to the end of the line is n factorial, which means that cancels with that. And we're left with n plus 3, n plus 2, n plus 1. I don't see the purpose in multiplying that out. If you had to, you could, but that's a grade 10 operation. I don't think you would be expected to multiply it out on an exam. I could be mistaken, but we're not going to here. N factorial over n minus 1. Okay, well, be careful because the n and the n minus 1 are not factorials. But if we expand the factorial of n, we can start to see something else happening. I'm curious, how many of you know that that's n minus 2 factorial? Just by seeing, so you're looking ahead, you're saying these two factors of n and n minus 1 are the leading factors in the numerator that are going to cancel. But to demonstrate that, n factorial is n times n minus 1 times n minus 2 times n minus 3 dot 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 times 3 times 2 times 1. And this is over n and n minus 1. These are not factorials. They're just factors. So the n cancels with the n minus 1 cancels with the n minus 1. And what are we left with? We're left with this, which is n minus 2 factorial. And we're learning this so that at least in today's lesson, you can get a bit of an introduction to working with algebraic expressions that have factorials so that we can solve equations involving factorials later, including later today. Okay, there'll be one equation that we solve algebraically. Any questions with A, B, or C there? All right, so permutations, I've already told you this. A permutation is an arrangement of items. A permutation is looking at a group of items, picking some of them and arranging them. Okay? So order is important. And if you use the fundamental counting principle, the importance of the order becomes apparent because you put those blanks in particular orders. Although you can use the fundamental counting principle for things in which order is not important, like the scores at the end of the soccer game or at the halftime of the soccer game. It doesn't matter whether team A was on the left side of the scoreboard or on the right side of the scoreboard. So the only thing that's different here about example 2 is the word permutation. You're expected to know in this example that when I say how many permutations of the letters of the word Regina are there, you're expected to know I'm asking you how many ways can I arrange all of the letters. So we count the letters 1, 2, 3, 4, 5, 6. And I suppose we could put 6 blanks and write 6 times 5 times 4 times 3 times 2 times 1. But I hope we have graduated to the idea that this will be 6 factorial, right? I'll make that point in your notes here in a second. When I take a look at the letters of the word Ashmont, there are 7 letters, so it's 7 factorial. And, you know, if you want numerical answers, and sometimes we do and sometimes we don't, just make sure I'm right here, that it's 720. I'm pretty sure it is. And the 7 factorial is the 5040. By the way, and this will only be important for Monday, I don't need to point out this now, but I'm pointing it out for Monday. Everything we're arranging has items that are different. If I asked you to arrange all of the letters of the word Wetaskiwin, you got a problem because there's W's that appear twice. I have to see the word on paper. There's at least some letters that appear twice. So if you were to take an arrangement and switch those two letters, those two W's, it's not different. So that makes things more difficult. But that will be Monday. So I think we know this. I think I've kind of told you this point already a couple of times. The number of permutations of n letters taken all at once is n factorial. The only thing that's different here is the way I'm saying it. I'm telling you the number of ways to put n books on a shelf in a line is n factorial. That's what this is saying. Let's take a look at the next page. What if we take fewer items? And you have done examples like this. This morning, and I forget what the exact question was, but Patrick and I were working on a question. I think we had 8 digits to choose from, and we were asked to form 4-digit numbers. So we were arranging 4 items out of the group of 8. This is different. Well, I'm going to give you some illustrations of what these problems would look like along with the notation. So first of all, if there were 7 different cookies, and I literally mean there's a coconut cookie, there's an Oreo, there's a snickerdoodle, there's a chocolate chip. I've lost count and it doesn't matter, but I have literally 7 different cookies. And I go into the kitchen and I say, Mom, can I have some cookies? And she says, you can have 4. Oh boy, I can have 4. I can have any 4 I want, but the question is not how many ways can I pick 4 cookies, how many ways can I eat 4 cookies? So if I pick the snickerdoodle, the coconut, the Oreo, and the chocolate chip, I could eat them in that order or a different order. And by the way, we would solve this by putting 4 blanks, and we'll do that in a bit. But this is the notation. 7p4, where 7 and 4 are both subscripts. 7 is the total number of items that I am allowed to arrange groups of, or groups from, and 4 is how many I am arranging at once. If there are 8 empty seats on a bus and 6 people get on the... Is yours got a typing mistake there? Does it say but in your handout? It does, okay. If there are 8 empty seats on a bus and 6 people get on the bus, how many different ways can they be seated? Well, there are 8 seats. I know you're not arranging the 8 seats, but you're arranging the 8 people. And when we learn, everybody, about combinations next week, there's a much better, cleaner way to think of this. But the bottom line is you have to arrange those 6 people in 8 seats, which means it's 8p6. And I would like you not, I've seen videos online and I've also seen things in textbooks that say pick. P is pick. It's not. Because when you pick items, the order doesn't matter. It's arrange. And I will actually use the word, I don't know if it's an actual verb or not, I will say 8 permute 6. So it's not pick. One final illustration here. How many 3-letter arrangements can I make using letters from the words Roxy Music? Well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 items there. If I want to arrange them in groups of 3 at a time, then it is 9p3. Right? That's what that notation means. And there's a formula, and this formula is on your formula sheet. And the next example, I hope, is going to illustrate to you why the formula is what it is and why it works. What this is saying is, for example, that last example was 9p3, correct? Is that what I just said? For the, Roxy Music in 3 letters. So this would be equal to 9 factorial over 9 minus 3 factorial. 9 factorial over 9 minus 3 factorial. I want to actually write this out. This isn't... Man, my brain gets locked in a certain thought, and I just can't get rid of it. 9 factorial over 9 minus 3 factorial. That's 9 factorial over 6 factorial. How many of you see that's 9 times 8 times 7. That's the point of the first set of examples, that this is 9 times 8 times 7 times 6 times 3 times 2 times 1. But this is 6 factorial. So you're left with 9 times 8 times 7. Okay, wait, just a second here. If I go back to that question, and I asked you this yesterday without the fancy words and notation, you would say, well, I'm going to need 3 blanks. How many different letters can I choose from for the first blank? You'd count them up and you would say 9. You'd look at the question and say, we're arranging those letters so it's not like I have an infinite number of each one. I'm moving them around so I can't repeat. You get the same answer, don't you? Okay. So that's the formula. We're going to solve example 3 here, which is a very basic question, in at least 3 ways. Okay. One of the ways is to go back to yesterday. We are taking letters of the word Ashmont, and there are 7 letters, yes? We're going to arrange them in groups of 4 at a time. In other words, everybody, how many different 4-letter arrangements do I have? Well, 7 times 6 times 5 times 4. 840. So that's using the fundamental counting principle. What if we used 7p4? Well, according to the formula, that's 7 factorial over 7 minus 4 factorial. And I mean, I really hope you see the result is going to be the same. But if you wanted to, and I don't recommend this, you could figure out what 7 factorial is. You could figure out what 3 factorial is. And if you take 5040 divided by 6, we sure better get 840. Can you confirm that, though, on your calculator? Okay, so 840. Well, sometimes we have tools that we use because they just make our job easier. And on your calculator, when you go to where you have your factorial, you will see NPR. So on my calculator, and I'm in the non-advanced mode right now, I would enter 7. I would go to my math menu, go over to the probability menu and choose NPR, and then 4. And before I hit equals, that doesn't matter, it's 840. I need you to understand, you do not need brackets around that. That function, NPR, looks to the left, grabs whatever's there, and locks it to n. And it looks to the right and grabs whatever's there and locks it. That doesn't mean if I did this that it's going to lock 8 to the right side of that. It's going to figure out what 7p4 is and then multiply by 2. So anyway, you can do that. And depending on the mode and the calculator and the operating system you have, you will be able to access it in one of your alpha menus as well. And depending on the mode you're in, I guess I might as well just quickly show this to you, and then we can move on. Oh, I am in Math Print. Am I wrong? Does anybody have a calculator that actually puts subscripts and you can put that? Can you hold up your calculator? Oh, it's the Cadillac of calculators. So you might have a calculator that has an operating system that when you access that, it actually puts subscripts down there, and you can fit the numbers in. Just like when you go squared, it puts a little box. Okay. All right, I just want to talk about the fact, if you use your calculator right now and go 0 factorial, what do you get? 1. It doesn't really fit the pattern of what we're thinking of for factorials. First of all, in this class, we are only ever allowed to take a factorial of a whole number. Okay? You're only allowed to take the factorial of 0, 1, 2, 3, etc. Why is it 1? Well, if I told you that how many different ways are there to arrange 7 items out of a group of 7? You know that's 7 factorial, don't you? It has to be 7 factorial. That's what we learned yesterday. Well, if I apply that to this formula, and I put a 7 here, here, and here, I'm going to get 7 factorial over 0 factorial. The only way I can get 7 factorial out of that is if 0 factorial is 1. So you need to know by definition 0 factorial is 1. By the way, and this is just because I see some of you poking around on your calculator right now, and I suspect at least 1 or 2 of you are trying something. (1.5 factorial exists at a higher level in math. Okay? Don't try to figure out what it means. But 1 factorial, 1.4 factorial doesn't. Okay, so there's a bigger thing going on with factorials than what we're using it for, and it's not important. It isn't as simple as odd decimals and even decimals, by the way. All right. Number 4, in a particular country, license plates consist of 2 different letters followed by 4 different digits. What's the total number of plates? Well, 2 different letters, 4 different digits would be 26 times 25 times 10 times 9 times 8 times 7. Are you with me on what I'm doing there? Different letters, different digits. 25 times 26, whoops. 25 times 26 for the letters times 90 times 56. That's just the way my brain operates. I'm just multiplying them in groups. You should be getting 3,276,000. Am I right? Okay. How would we do it using permutations? Listen, we still use the fundamental counting principle. You still need to have 2 digits, or 2 letters and 4 digits. This is so much cleaner. That's it. That's the answer. That might even be the answer in a multiple choice question. 26p2 is the number of ways to arrange 2 letters out of a group of 26, and multiplied by 10p4 is the number of ways to arrange 4 digits out of a group of 10. I like, well, I'm trapped in the past in many ways. Scientific calculators, before we had graphing calculators, scientific calculators had a button right there that said NPR. It had N factorial. It had NCR. It had all these things accessible. And with these calculators, you've got to go poking around in menus. I'm going to go under the assumption here that you can enter this. I'll do this one, just this one. 26 P2 times 10 P4. Oh, geez, I just can't stand that. Give me a second. As a teacher, I can't stand that because you can't see what I've just typed. Okay? So it's 26p2 times 10p4. And you don't need brackets. I know the spacing makes it look like maybe the calculator is going to multiply 2 by 10. It's not. That's it. Let's move on. I think this is the final example. Am I right? So we will have lots of time today to practice with the new material, which you'll find is a lot of repetition from yesterday, and you can continue to work on yesterday's material. Solve this equation algebraically. And this might be a little 2 or 3 mark written response question. In order for us to solve this, we have to look at NPR on our formula sheet as n factorial over n minus r factorial, and customize this equation using that formula. So we're going to have n factorial over n minus 3 factorial equals 2n times n plus 8. So you've heard me explain my philosophy with equations before. The reason why you square an equation that has radicals is not because you've memorized that. It's because squaring it will get rid of the radicals. The reason why you multiply rational equations by denominators on both sides is to get rid of the denominators to make it easier. We have just taken a huge step in going from something that's almost indecipherable, not useful, NP3, to something that we can handle. But we still don't want to work with an equation that has factorials. So how can we get rid of the factorials? Well, recognize that n minus 3 factorial is a smaller factorial than n factorial, meaning it's inside of n factorial. So we're going to expand n factorial to expose the n minus 3 inside of it. So we're going to have n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1 is equal to, I don't see any reason why we can't just multiply this through right now. And the reason why I did is I'm crushed for room there anyway. So 2n times n is 2n squared. 2n times 8 is 16n. This is, of course, over n minus 3 factorial. Which, as I said, a smaller factorial will always be a factor of a larger factorial. Always. So these cancel. What we are left with is n times n minus 1 times n minus 2 equals 2n squared plus 16n. So we have to expand that out. This, if you don't see it, this is going to turn into a polynomial equation from way back in February. If I expand this out, I get n times n squared minus 3n plus 2. Take a minute and absorb what I've just done there, mentally absorb it. I'm going to multiply that n in now and get n cubed minus 3n squared plus 2n equals 2n squared plus 16n. It's a polynomial equation, so I need to zero the equation. Can you double check my algebra / arithmetic there? Looking good? Okay. Oh, geez, thank you, Janessa. Absolutely, it should be 5n squared. Good eye. Can somebody tell me why, if you asked me, I would say you're not allowed to divide this equation by n? I mean, mathematically, I could divide both sides of the equation by n. Why am I not allowed to? And we've had this discussion before. It gets rid of a factor that's variable. Like, would you agree right now with this equation that n equals 0 is a solution? Just looking at it, n equals 0 is a solution. Don't write this down. If you go, wow, I'm going to divide everything by n, you will have eliminated a solution. And let's not worry about the fact that n equals 0 is extraneous, and I'll tell you why it's extraneous in a second. You cannot divide out factors that have variables in them. It's why even if you factor out a common factor in an equation, I've tried to impress, and you just leave it there. It's not hurting anybody. Just leave it there. So what do we do instead? We factor the n out and have n squared minus 5n minus 14 equals 0. And now I can factor that quadratic. So there is our cubic polynomial equation in factored form. You can see over here that n is equal to 0 for the first factor, n is equal to 7 for the second factor, n is equal to negative 2 for the third factor. Why is that extraneous? Well, n is the number of items, and you can't have a negative number of items. Why is this extraneous? Well, n is a number of items. You can have 0 items, but why in this question is it extraneous? You know, Will?
N minus 3.
Oh, yeah, you'd get an, oh, I didn't never ever thought of that. If you put in 0 for n, you're going to have n minus 3 up here. You'll get a negative number factorial, which may or may not exist on your calculator, but it doesn't mean anything here. The other way to look at it is that that would mean we have 0p3, and I'm asking you to arrange 0 items. I'm asking you to arrange 3 items out of a group of 0, and that can't be done. We'll talk about what really happens in a second. But anyway, the only number that makes sense is 7. And that means that 7 is the answer to the question. Now, if you had, just briefly, if you had this question as a numerical response question, which I think is kind of a cheesy question, I just think it's too basic, given what I'm going to show you. You could put in for y1, oh, I had it right there too. You could put xp3, and for y2, you could put 2x times x plus 8. You're not going to solve this graphically because your calculator just has a panic attack when it comes to graphing permutations. It can't do it. You might see little dots in different places. You're simply going to go to your table. You'll set up your table to start at 0 and go up by 1. And you'll go to your table, and you will be looking for where y1 and y2 are equal, and it happens at 6. Didn't we get 7? Oh, see what I've done there? We've got 2 plus 8. It should be x plus 8. And we go to our table, and it happens at 7. Okay. Now, it does happen up here at 0 because, and this does make sense if we step outside of a Math 30 classroom for a second. How many ways can I arrange 3 items out of a group of none? I can't do it. It's not one. It's not there's only one way to do it. It's just an impossible situation. So we say the number of ways is 0. And it turns out that when you put 0 into the other equation or the other half of the equation, you'll get 0 as well.